All right, one of the key things about the cell matrix architecture is this idea of having two modes of operation, C and D. And on the cell matrix, in addition to a D input and output, we have these C lines. And the C line controls the mode of the cell that's receiving a C input. And if C equals 0, we're in what's called data mode. And if C equals 1, we're in control mode, or code mode. In data mode, things are just pure data processing. The truth table takes the 4 D inputs, looks them up, generates outputs to the D outputs, and also the C outputs. When C equals 1, we're in a mode where we're reading and writing a cell's truth table. So the incoming value of D is used to populate the bits in a cell's truth table, and the bits, as they're being overwritten, are sent out the corresponding D output. So that's the basic control mode operation of a digital cell matrix cell. How do we map this over to the songline processor? Well, back to our three-sided cells, just for consistency. So we have D and C on both sides. And this is all nearest neighbor to nearest neighbor. And everything we've talked about so far is assuming that your C input is equal to 0. Well, what we would like is, if your C input is 1, we'd like to take these D inputs and somehow use it to populate the function stored inside a cell. Now, in our discretized version of the songline cell, we have 64 times 64 times 64 rows in our truth table, and we can order those, and we can program this exactly the same way we do a regular truth table in a digital cell matrix, which is we just sweep through the truth table in some particular prescribed order, and we pull out the voltage levels. And those voltage levels come out of the D line and go into the D line of the neighbor as the values in the truth table are overwritten. So let's do our simplified version again. Let's just look at a function of two variables and a single output. So we rasterize the input space in some sense. Here's all the possible combinations of x and y discretized to within 1/10, just ranging from 0 to 1. And we can impose an ordering on how this table would be laid out. And this string of values is simply what we ingest through a D input when we're in C mode. And the incoming values are plopped into this table's entries. And as we're overwriting values, the previous values come out of the D output and are available to whatever neighbor is doing the programming. So we can do all the stuff that we do on a cell matrix. We can read the contents of a cell, we can copy it to a neighbor, we can do a non-destructive read by feeding back, we can do parallel replication, Medusa circuits, all the stuff that we're used to doing on cell matrix, we can do on a songline processor. One of the kind of unfortunate artifacts, though, is that we do have this discretization, and we have to have some notion of how quickly we're sweeping through this table. Now, when we talk about implementation in the next video, we'll see a few possible ways that maybe we can get away from this. But for now, for the sake of simulation, this is exactly what's happening, and we can just work with that. All right, so we have C mode behavior, but we've still got one more thing we have to do. On the cell matrix, C mode is binary. It's on or off. 1 is C mode, 0 is D mode. What do we do with the fact that on a songline processor, C is a continuous valued variable, a real valued variable? Could be anywhere from 0 to 1 or 0 to 5 or whatever range we break it into. In our case, 0 to 63. So what do we do with these values? Well, we could just say if it's below 32, we're in D mode. If it's above 32 or equal to 32, we're in C mode. We can just clip it and make it binary. But why take something that's already gloriously analog and force it into a digital realm? So what we do is we say that C mode is no longer just on or off, it's a gradient. So C equals 0, that's pure D mode. and I'll stick with 5 volts. C equals 5, that's pure C mode. C equals 4, that's mostly C mode. C equals 2.5, that's half C, half D. C equals 1, that's mostly D. Alright, what does this mean, mostly C mode, half D mode? We simply use C to weight a combination of C and D mode behaviors within the cell. So what does this mean on the output side? F of whatever, let's just say inputs, where your inputs could be more than one value. So F of your inputs is equal to, well, in a binary sense, it would be, let me write it like this. So here's the output. In a binary sense, it would be F of n if C equals 0. And it would somehow be the function itself if C is equal to 5. What do we mean by the function itself? We go through the table that stores the values of F and we actually read out those values in succession. So it's sort of sweeping through all the possible input values and taking the outputs. So if C equals 0, the output of a cell is just whatever the function maps that input to. But if your C is 5, if you're all the way in C mode, your output is actually the function itself. Some serialized coded representation of that function. And so we simply make a weighted mix and we say the following: out equals F of n times C minus 5 plus F times C over 5. Where this F is the function itself. So if C is 0, 5 minus C. If C is 0, this becomes a factor of 1, the output is just the function value, and 0 divided by 5, this component does not contribute. If C is 2.5, this is 2.5 over 5, so you get half of this. 2.5 over 5, you get half of this. And when C is 5, this goes to 0, no contribution from the function's output value. C over 5 is 1, full contribution from the function itself. So that's specifying the output value, and the input value, well, the incoming D line is used to modify the truth table, the function that's stored inside a cell. So the function itself is again a mix. If C equals 0, it's just the original function value, the function. If C equals 5, it's the input. And so F is equal to, and it's the same formula, 5 minus C over 5 times F plus C over 5 times the input. So if C is 5, this goes away and the function itself comes from the input. In other words, the D input coming into a cell becomes the stored lookup table for that function. As C drifts down to 0, this component diminishes, this component increases, and eventually our function is just equal to whatever the function is. In other words, it doesn't change. So we have this blurred range of C values between 0 and whatever the maximum is, 5 volts in this case. That gives us a composite hybrid behavior, some mix of D mode behavior and C mode behavior. Is that good? I don't know. Most of the circuitry that I've done so far using C mode pegs C mode one way or another. But some of the machine learning work that we're starting to do with pattern detection and trying to reinforce learning based on success of pattern detection taps into this idea of using the C mode to control how strongly a cell's function is modified. And that may be a place where this variable C mode hybrid behavior actually turns out to be really beneficial. Final comment on here is that this is basically sort of like functional analysis. In functional analysis, we can take a function and we can operate on it the way we normally operate on numbers. We can talk about doing calculus type things on functions. We can of course add functions, subtract functions, multiply them, compose them, and so on. And that's kind of what we're doing in the Songline processor. When we switch into C mode, we're no longer just taking an input voltage, changing it and generating that as an output. We can actually take a function by putting a cell in C mode. We can take the function itself and somehow move that out of the cell, transfer it around, do operations on it, multiply it, adjust it, analyze it, and then at some point actually turn that back into an operational function by putting it into another C mode cell. So that's a bit of what the SLP is tapping into. All right, let me talk in the next video a little bit about how we could possibly implement this. Mostly to talk about some of the issues with this, but we'll do that in the next video.